Today I'm going to talk about the differential form of the conservation of momentum equation. I'm going to start this by writing the Newton's second law, okay, dl dt, where this L is the momentum, or the linear momentum to be more specific, okay. And what I can do is I can take the definition of the momentum into account, and this will be simplified to d dt of m velocity vector, okay. So if I have a closed system, which means that no mass crosses the boundary, what I will obtain is the summation of the force vector will be equal to m dv dt, right? So if I consider a small fluid particle, right, that is the entire approach by having a differential form, as we discussed in the conservation of mass equation as well, okay. And basically it's going to be the volume, and as we mentioned, it's going to be delta x, delta y, delta z will be the volume of that particular small fluid particle, right? Actually, if I go up and look at this, you do know what this means, right? This is the a acceleration at a particular point, so f is equal to ma, so we do know that, okay. So what I'm going to do now is I will separate the sum of the forces into two components, okay. The first component is I'm going to call this body forces, okay, and the second component that I have will be called the surface forces. So let's go over what body forces are. Body forces are the forces that's applied to the volume, okay. So if I think about it, the weight of a control volume is a body force, right? Because mg, right, m is equal to rho times v, right? So if I write the weight, which is mg, and I write the definition of density into here, it's going to be rho times volume times g, right? So it's a function of the volume. That's why it's a body force, okay? On the other hand, surface forces are the forces that is applied, as the name suggests, onto the surface or the area, okay. So if I look at for instance, the pressure force, if you remember, force is equal to pressure times area, right? It's applied to the area, while this is applied to the volume. So it's just a simple classification of different type of forces. It's not necessary to have this specification, but it will make my life easier for this particular approach, okay. As I mentioned, the body forces, if I write the body forces, this can be electromagnetic forces as well, which is not as common. You can, right? But it's going to be m times gravity vector, because gravity has a direction, right? So if I write the way that I define this, it's going to be the density times volume of g of x I plus g of y j plus g of z k. Now, let's take a look here. What do I mean by gx, gy, gz, or I, j, k? So basically what I mean is the gravity has components. It's a vector. It has components in the x, component in the y. This is the x, this is the y, this is the z, okay? So if you align your coordinate axes, let's say that the z direction pointing up, then gx will be 0, gy will be 0, and gz will be minus g. And if I'm using SI, that will be minus 9.81, right? Okay. The second type of force is the surface forces, okay? And unfortunately, this is a little bit more involved than the body forces, okay? And this is related to the stress tensor, okay? And the tensor is a two-dimensional, so if I write this over here, it's going to be like the tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, and tau zz. So it will have 9 components over here, as you can see, right? So actually, let me try to do a better job here. Right. So this is my stress tensor, and this is related to the forces, okay? Now, the next thing I'm going to do will look a little bit more complicated, so just hang in there with me, okay? It will be accomplished. It's not too bad, okay, but it's a bit mathematically dense, okay? So what I'm going to do is I'll take the exact same approach that I did for the conservation of mass. What I did was I take my small particle, volume of that small particle, in a small domain. I will represent this as a cube, right? So I draw myself a nice cube, okay? And when I was doing this in the conservation of mass, what I did was, if you remember, I did my derivations in the x direction, and I said that, hey, you know what? This is symmetric, so the final answer will look symmetric in all the dimensions, right? Looking at these 6, I will do the same approach. I will only consider things in the x direction, okay? Then depending on how I proceed, you will see that I obtain something symmetric, so I can use similar approach for y and z directions as well. So I'm going to start with the low-hanging fruit, or the easier ones. I'm going to call this force number 1, okay? And on this surface, then what I'm going to have is well, force number 2, okay? What I mean by forces, stresses times the area is equal to force. That's what I mean by that, okay? And then I'm going to have one of them down here at the bottom of this, and I'm going to call this 4, okay? I'm going to have one in this front surface, and I'm going to call this 3. I'm going to have one at the top surface. I'm going to call this 5. And I'm going to have one at the right back there. And I'm going to call this 6. Okay? Like I mentioned, this may look a little bit more complicated, but unfortunately I have 6 components that will contribute to the stresses, or multiplied by area, forces in the x direction. So now the approach that I'm going to take will be actually fairly identical to what I did for the conservation of mass. Okay? At the center of the cube, everything is defined. The velocities, the densities, these shears are defined at the center of the cube. So what I'm going to do is I'm going to transform them from the center of the cube to the individual faces that I do obtain. Okay. All right. So let's start by the force, or rather, the force number 1. Okay. First of all, this will be tau xx, right? Because if I define, this is x, this is y this time, you can change this, obviously, it's not a function of how you determine it, as it's symmetric, but I'm going to take this x, y, and z in this particular manner, okay? This is the number 1 will be tau xx, but I said that at the center of the cube, I defined this as tau xx. If you remember, we did a similar approach in the conservation of mass. Then I'm going to add, because I'm going in the positive, the x direction, the rate of change of tau xx in the x direction. The reason why I call this x is in order for me to go from the center of the cube to the face where I have the force number 1, I travel in the x direction, okay? And the distance that I travel between the center of the cube and that surface is basically delta x over 2. Okay, and actually, let's be for a good measure, let's just write here delta x over here. This is delta z, this is delta y, right? From the way that we defined. Okay, so this is the one, this is the stress though, right? This is the stress. What I want to do though is I want to go ahead and multiply this by the area that this is acting on, so I can obtain myself a force. Okay, and this will be basically the depth is delta z and the height will be delta y for surface number 1. Okay. While at it, I want to go ahead and write 2 as well, and this will look again very similar to conservation of mass. So this will be tau xx, this time around minus, because I'm traveling in the minus direction, delta x, times the distance that I travel between the center of the cube and the face number 2, right? And if I multiply this by delta y, delta z, what I'm going to obtain myself is the area multiplied by the stress. Note that this is a force balance. That's why I'm trying to obtain the forces as opposed to the stresses. Okay. So what I'm going to do now is I'm going to go ahead with the force number 3. And the 3 is on this particular front side of the cube. Okay. So one thing that we have to establish in here is this is going to be tau zx. Okay. And I'll show you how we define these. You may remember this from this other course as well. If I have a tau, let's say I and j, okay, this will be the normal to the surface that is acting on, and the j will be the direction, Okay, so if I write that, so it's going to be tau zx, and I travel in the positive direction when I go from the center of the cube to the face number 3. Okay, so it's going to be tau zx del tau zx del, let's take a look together. Okay, so what direction that I'm traveling from the center of the cube to the face number 3? You do see that I travel in the z direction, right? So that's why this is going to be z, and the distance that I travel between the center of the cube and that point is, or rather that surface is, delta z over 2 times delta, then multiplied by the area to obtain force number 3. And if I scroll up, you will see that the area is defined by delta x is the width and the height is delta y. So this is going to be delta x, delta y. Okay. While I'm at it, I also want to do force number 6 because those 3 and 6 are pairs. So I'm going to go over here and I'm going to in the 6 say that it's going to be tau zx minus del tau zx del z times delta z over 2 times delta x delta y. Okay. Okay, so then the last one that I have left with is, let's take a look on from my figure. Okay, I defined it as 5. So at the very top surface, it's going to be the 5. Okay, so let's write 5. In the 5, what I'm going to obtain is it's going to be tau yx. Okay, if you scroll up, you will see that the normal to the surface that this force is on, or shear stress is on, is going to be this normal to that is going to be y, right? And also the direction of the force is x, so that's why I write tau vx. Okay, plus the rate of change of tau yx in the y direction, because I travel in the y direction when I want to go to the face number 5 from the center of the cube, times delta y over 2 is the distance in the center of the cube and that particular surface. Okay, and if I go up now, the area will be delta x will be the width, and into the page is going to be delta z. So it's going to be delta x, delta z. Okay, last but not least, I'm left with number 4. So let's write this down as well. So it's going to be tau yx minus del tau yx del y times delta y over 2 times delta x delta z. Wow, that was some effort, right? Okay, good. So we accomplished all these 6 of the forces that will be aligned in the x direction. Note that these are only ones in the x direction, okay? In the y direction and other directions, we are going to have different ones. Now, I want to obtain, if you remember, I want to obtain the summation of total surface forces. So let's call this F surface, right? So let me see which pairs am I going to subtract the net. So what I see, the way that I define is, if you look at it, it's going to be 1 minus 2, right? Because 1 is in the positive x direction, 2 is in the negative x direction. I'm just going to be 3 minus 6 and also 5 minus 4. Okay, so let me write what I just said. Okay, so it's going to be the force number 1 minus force number 2. Okay, plus it's going to be force number 3 minus force number 6. Okay, it's going to be force number 5 minus force number 4. Okay, so this will be the summation of all these 6. Okay, now, so let's take a look at the rest. Basically what I'm going to do is, if you look at it, I'm going to have 1 minus 2. So let's just look at these 2 first ones. Okay, you can see over here that if I'm subtracting, okay, this term times delta z delta y, there's a minus tau xx delta v delta z. So you do realize that these 2 forces will cancel each other, right? It's very similar to the conservation of mass. Then what I'm going to do is I look at the second term over here, this, and there's a minus and another minus, so that will be minus becomes plus. So these 2 second terms will be added up, right? Okay, yes. So I'm going to do basically write that. I'm just analyzing 1 minus 2 at this point in time, okay? And basically, as I mentioned, this is going to be del tau xx del x. So it's going to be delta x times delta y times delta z plus, actually it is the same, del tau xx del x. Excuse me, there's a delta x over 2 over here. Delta x over 2 times delta y, delta z. So then if I continue with that, you'll see that they are the same. So I'm going to multiply this by 2. So it's going to be 2 times del tau xx del x, delta x over 2, delta y, delta z. Those will cancel. Delta x times delta y times delta z. What is that? Volume, right? So then 1 minus 2 gave me that a simple term like this. Del tau xx del x times the volume, okay? Now, I'm not going to repeat the same analysis for 3 minus 6, okay? If you do 3 minus 6, you will see that I'm going to obtain myself del tau z, del z times the volume. And if I do 5 minus 4, from the same logic, I will get myself del tau yx del y times volume. I'm simply going to go ahead and write it, okay? So then, if I do that, basically the second term and the third term together, so let's call this Sx, because S is the surface force, only in the x direction, I get myself del tau xx del x plus del tau yx del y plus del tau zx del z times the volume. You can see that I obtain only in the forces in the x, okay? So obviously there will be forces in the y and there will be forces in the z as well, okay? But let's remember what we were trying to accomplish in here, okay? Let's go back to at the beginning of the module, doing this entire mathematical analysis. Is basically my goal was to obtain this summation of the forces, and I separated into two: body force plus the surface force. The body forces were right over here, right? And the surface forces is the fancy one that I have derived after all this effort. Is rho v, this is m, times the acceleration. I'm going to call this du dt, okay? And this will be rho volume gx. What I mean by this is the body force, right? This is the body force in the x direction. Body force in x direction, okay? And this will be plus basically this Sx, right? So let's just add them up. Del tau xx del x plus del tau yy del y plus del tau zz del z, and let's not forget that this whole parentheses is multiplied by the volume, okay? So basically you can see that this is how it is established. One thing I would like to do now is basically go ahead and cancel by volumes, because all three terms are the first component of the conservation of momentum equation is this: rho gx plus del tau xx del x plus del tau yx del y plus del tau zx del z, okay? And if I can go ahead, and you can practice at home, I'm not going to do it here, is the second component. So this is the x. Now if I write in the y, it's going to be symmetric. So this is going to be d. Instead of u, I'm going to call it v. This is the velocity in the y direction. It will be equal to rho times gy, right? So this time around, I will actually, if I practice this, you will see that I'm going to obtain tau xy del x plus del tau yy del y plus del tau zy del z. Again, if I go ahead and do the analysis for the third one, so I'm going to have rho times dw dt will be equal to rho gz plus del tau xz del x plus del tau yz del y plus del tau zz del z. Okay, we obtained these conservation of momentum equations in the differential form. The only part that we didn't really address so far is these acceleration terms in the x, in the y, and in the z directions, okay? So actually we did cover these in the fluid kinematics section. So I'm gonna rewrite these from that section, okay? So all of them will be multiplied by the density. So I'm just gonna write the du dt component, and that will read as del u del t plus u del u del x plus v del u del y plus w del u del z. dv dt will be also equal to del v del t plus u del v del x plus v del v del y plus w del v del z. And the last component will be dw dt, which is the acceleration in the z direction, will be del w del t plus u del w del x plus v del w del y plus w del w z. Okay, so basically you need to insert these acceleration terms into the corresponding places. Okay, for instance, du dt needs to go over here. Okay, unfortunately the equation is very long, so I'm not going to rewrite them, but this is the final equation for the conservation of momentum in differential form.